that's in essence a ground. So I'm grounding it, by touching it, I'm large enough compared to this that I can take excess electrons and not really notice. If there's a whole lot of charge there and I touched it, well, when my finger got close, if the electrons are really trying to get away from each other, they'll jump one way or the other, depending on which one's negatively charged. All right. Take a look at the glass. All right, so I'm going to do this. I'm going to bring it closer, and that was sad and pathetic. All right, there we go. Now when I touch it, only the electrons in the local area will actually transfer. So that's why I was rubbing it along there, just so that it had access to more electrons. And now go back to my PVC. And I bring it closer. And the leaves come towards each other. What does that tell you?
It's more negative than the PVC is.
Say it again?
The box is more negative. It has more electrons, so where the PVC is less negative, so it'll the electrons will attract more that way.
Okay. If this is negatively charged, one made more negatively. All right, start from the beginning again. You said that.
I said that has now more negative charge than that does, and to equal it out, it wants to give some of those negative, or those electrons to the PVC.
But if this is flooded with negative charges, and I bring negative, so right now the electrons are spread out however they need to be.
Oh, okay.
If I bring something more negatively, I bring another negatively charged thing near it, it would chase some of these electrons up here down below, and they would spread out a little bit more. But the fact that it came together, all right, so let's work under the assumption this is negatively charged. If I bring this towards the ball on top, any electrons in the ball are going to want to go down into the leaves. So why would that cause the leaves to move closer?
Opposite charge.
When I rubbed the glass and silk, the glass became positively charged. When I touched the glass to this, it drew electrons off of it. So electrons went into the glass, and so this was now positively charged. When I bring the negative charge towards it, it chases the electrons here down into the leaves, making them closer to neutral. They're still positively charged, but making them closer to neutral. And so before, when it was negatively charged, I touched it and they came together because I basically absorbed the excess electrons. Now, if I touch it, it goes back because I was able to give it electrons. We also had a couple of vocabulary words there. Conductor. Insulator. There's another word that's not blanking on right now. Right here. Yeah, this is the two main ones. Conductor, the electrons flow. I didn't put the term easily there. in quotation marks. Easily, it's later, the electrons do not. Later on, we'll sort of get into what makes the electrons flow more easily than others. Nothing is a pure insulator, nothing's a pure conductor, but they're close enough. And then semiconductor is somewhere in between. Let's bring up the big gun. A Van de Graaff generator. That's on, let's crank it all the way up. All right. When I turn this on, the belt is going to start to move. Down at the bottom, there's sort of there's a fuzzy material down there, and the belt's going to slip slightly, causing there to be charges transferred. What happens is that actually negative charges get transferred onto the felt, and so the belt becomes positively charged. When the positively charged belt comes up to here, it's going to pull the electrons off of this onto the belt, and the electrons will come down here and then be basically drained away, and it repeats the process. So it's going to constantly be pulling electrons off of this. And so the question is, what is going to happen? Why don't we just start out with that? What's going to happen when I turn it on? So you were saying they're coming together?
Yeah.
Are we gonna go with Gina? Feeling good? Just blank stares.
I'll be contrary and say it'll like kind of try and get off of the ball.
All right, so I guess our three choices are: it'll get stuck harder, it'll try to come off, or nothing happens. The follow-up question after we see what happens is why? Now, the reason I'm using my foot to turn that on and off is sometimes that gets a little bit charged also, and I have shocked myself trying to turn it on and off by hand. All right, so way to go, Zachary. Zachary.
Doesn't matter, I've been asked that question my whole life.
Okay. You signed your paper, Zachary, right?
Yeah.
Okay, Zachary. Why?
Because it's pulling the electrons off of it, meaning there's a much larger positive charge. And it has to do with the like charges push each other.
Right. Okay, you're almost there. I'm not gonna counter anything that you've said so far, but I feel like there's a piece missing. How did they get to be like charges?
Are the electrons also going in and being taken away from the disk?
The pi pan?
Since they're
Yes.
touching?
Yes. The pi pan is metal. Metal is a great conductor. In general, if you ever see in a problem it says there's a piece of metal, think conductor, unless they state otherwise. When the ball becomes positively charged, it wants electrons, which means that it's going to deal with, which means when this positive charge is going to want electrons. The belt is still going to be taking electrons off of it, but it's looking for a source of electrons, and that's the pi pan. So it's going to start pulling from the pi pan. So the pan will become positive, ball's positive. Now there are like charges, it will repel. In theory, you could get it to hover, but I doubt it's actually practical for that to work. So I have the tape. have a spring, hopefully not attached to anything. There we go. So now, oh, I probably should neutralize it because this is not summertime. So now this is positively charged. The electrons, the spark would have gone from here to there. And I can discharge it just by touching to something else. Occasionally I have students who like the actual feeling of that. So if anybody in the group wants to discharge it by hand, you're welcome to it. There's a smaller piece of string, that'll work better. So now what I'm going to do is I'm going to take this piece of string to it. And what's going to happen is, let's put it at the very top. So what's going to happen now when I turn it on?
I'm gonna guess something similar.
It's going to,
Well, not, it's gonna be the opposite of what happened the first time.
so it'll get stuck more.
Yes. I'm gonna go with this.
Will we go with Gina again? Is Zachary going to be contrary?
I think it'll wave like a flag, like it'll try to get away, but it can't because it's taped down, so it'll.
Yeah. If there was enough to, if it's going away and if there's enough to overcome the tape, and it's either cheap tape or it's a lot more powerful than I thought, but let's see what happens. There we go. So I'm trying to get away. Now this is neutral object here. I'm going to bring it closer to the string. And so think in your head what's going to happen when I bring it closer to the string. And we also have some sort of indication of humidity by how fast that thing collapses. But why did the neutral object cause it to get attracted? Let's go back to something Sean said earlier. Did you want to go for it again?
Yeah. So the string is more, there's no electrons, it's positively charged. So it causes a dipole in that neutral object and pushes all the electrons into one spot, like closest to the string.
So we got this positively charged. We have a positively charged string here. Then we have this neutral object towards it. This has electrons and protons in it. It's neutral, so we have just as many protons as we have electrons. As it gets closer, the electrons are attracted to this. It's the electrons that move, flow easily. So the electrons will then start congregating over here. If the electrons are moving that way, that means I'm left with positive charges over here. A net positive charge. I will say not all the electrons flow. I think you said there's no electrons at one point. There's,
Oh, well, I said in the string there's no electrons.
yeah, but there's still electrons in the string. It's not that powerful. But now this is what is called a dipole, where it is, although it's technically neutral, it's not evenly distributed positive and negative charges. So now the positive charges are farther away, negative charges are closer, and there's an attraction. So I'm going to turn it on. The string should go up again. Okay. String should go up again. This time I'm going to touch the ball, the wand to the Van de Graaff generator. Think about what should happen. And then I'm going to take my wand and bring it closer to the string. So it's repelled by it, I pull it back, now attracted. Neutralize that again. Hit one for a second. Supposed to repel. When I do it all. So, a different phenomenon there. Come on, there we go. The string was supposed to be repelled after when I touched this, it would make this positively charged. This string is positively charged. Electrons would track on somewhere. Alright, so we'll ignore the part that I was not expecting. Why was the string bouncing back and forth? Neutral. So I put it on the metal, just. In case it goes badly, I probably should use my left hand for this. I'm gonna turn it on, put my hand near it. Rubber gloves and insulator, this is to protect myself. There are times, depends on how good the belt is and how aligned it is, but I potentially am gonna feel the hairs of my arm start to move. But if I did not have the glove, it would hurt. My first year here, I was doing the Van de Graaff generator. I had not found the long one, we had a very short one, and very nervous about playing with electricity. Had it up about halfway, and after I'd done the demo, a student goes, "Crank it up, Dr. Fox, crank it up!" I said, "No, I don't think so." "No, come on, crank it up!" No, I'm not comfortable with that. All right, I'll hold the wand. Okay. So he's holding the wand like this, because of the way the base was. A spark jumped from here to his finger, about that far away. That lesson was learned. Let's get this ring off. All right. Not good enough insulator. All right. All right, so this was neutral. I brought it towards it. It suddenly gets sucked towards it and then gets shot away. What happened?
The opposite charges attracted it, and then once the styrofoam was on it, they became like charges and then it repelled.
Yep. And just for the language, a dipole was created. Now, this does indicate one other aspect of charges here. Oh, Zachary?
Just, how do you spell dipole? Is it just D-I-pole?
Yes.
Okay.
And at this point, we have only one kind of dipole. It's an electric dipole. Later on, we'll have magnetic dipoles. So, for context, you'll know I'm talking about the electric dipole.
And that just means that there's electrons on one side and positive charges on the other side.
Yeah. A water molecule is a dipole because it is neutral by itself, but the positive charges tend to be on one side and the negative charges on the other. Thus, earlier about what happens when a neutral charge is brought near a positive charge, part of it depends. If it is a conducting material or conducting well enough, then you'll create a dipole and there'll be an attraction. Other questions before we get into some math? Because, you know, if we don't do math, I imagine you'll go through DTs. All right, let's do some math. The fact that the dipole is attracted, what does that tell you about the force between charges? Or the relationship of force between charges and the distance?
The negative charge is stronger. Like it has a stronger pull.
Why?
Because it's, like in that diagram, the negative part is closer to the,
So the closer it is, the stronger the potential attraction. So whatever equation we have for force, as R gets bigger, the force should, as R gets bigger, the force should get smaller, or as R gets smaller, the force should get bigger. And fortunately, we have such an equation that does this. So I'm first going to write up the version with ignoring direction, and then we'll bring direction into it. Because force is a vector, therefore it